Alrighty, here, let's see how this works out for us. Okay, here's the practice test for the pre-calc Unit 4 test. These first group items here are true, false, and they are all true except part C, but let's explain a little bit. Natural log of E always equals 1, that's an identity. This is also kind of an identity here. A to the log base A of B always equals B. It's sort of that's kind of a snail within a snail kind of a thing right there. It's kind of hard to demonstrate why that's true, but you just learn to recognize that if the base here is the same as the base of the logarithm, then whatever that argument is, that's what the whole thing equals. Okay? Here's an example of one of those logarithm properties where the coefficient multiplying the log turns into an exponent, and AB to the third power is the same as a to the third and b to the third. So it's the sum of those two logs. Here's another log property here. It's that same rule actually, but now I'm going the other way. So I'm taking this exponent of e and writing it as a coefficient of natural log of e. Well, square root of x times the natural log of e equals just the square root of x, because natural log of e, as we say right here, equals 1. So this is multiplying the square root of x by 1, which is the same as saying x to the 1/2 power. Last but not least, here in this group, these two functions, f of x equals log base 3 of x, the inverse of that function is the exponential function base 3. So that's what this means. F negative 1 is the inverse of f of x, and that base of 3 as an exponential function is the inverse then of the log base 3. Okay, let's move on to these graphing problems here. Here's a decreasing exponential function. It's decreasing because the base there is a number less than 1, and it has been shifted up 2 units. So there's my horizontal asymptote at y equals 2, and it goes down. All right, it's decreasing. The other graph is a log function. The basic log graph, if you can see this dotted line right here, that's a kind of a basic log, natural log of x function. That's what it looks like. So I've done 2 transformations to this equation. I've flipped it over the x-axis with that negative sign right there, and I have shifted it to the right 3 units. So this graph, if you imagine it flipping it over the x-axis so that it's coming down like this vertically off the positive side here of the y-axis, and then and crossing over, but then let's shift it to the right 3 units for this x minus 3 part. So that's what it looks like down there like that. Okay, moving on. This problem right here, this carbon dating problem, all right, this equation is saying that, okay, we have this big number here times natural log of this fraction. This fraction represents how much carbon-14 we have now compared to how much we had when the thing started. So when it was created, I guess you could say. Or at least when it stopped creating more carbon-14. I guess it just stops after a while. So then the tree branch dies, or the bone of the animal is sitting there, and now it only has 10% of what it started with. So the top number is only a tenth of what the bottom number was. Well, 10%. It doesn't really matter what those numbers are. If the ratio between the top and the bottom number is 10%, then this thing just is 0.1. So all I have to do is use my calculator to multiply natural log of 0.1 times this number right here. And that gives me this big number here, 19,864.4 years. That's how old this artifact is. Okay, let's do these evaluating logs. This is log base 10 of 10 to the 1/2. All right, so that just gives me 0.5. It's just that exponent when the base of the log is the same as the base here. So, right, so there's that. This is taking the natural log of 1. Natural log of e equals 1. So this inner natural log thing is equal to 1. So natural log of 1, all right, that equals 0. E to the 0 equals 1. It's the snail pattern there. This is log base 3 of 1/9, and so 3 to the what power equals 1/9, and that power is -2. Okay, let's do the next one. Writing log base 3 of 4 as a using natural logarithms, ln, or lateral logarithm, all right, Well, you would take the natural log of 4 divided by the natural log of 3. All right, so the base goes on the bottom. Maybe that's the easiest thing to remember, base on the bottom. And that's that page. We're going to flip it over now. Okay, so expanding this crazy-looking log expression here means we've got log of the square root of p plus the logs of q to the 5th minus log of the cube root of r plus 1. All right, so all of that stuff, these two things are products, so we're going to add those. This is a quotient, or this is the bottom of the fraction, so this will go be subtracted. All right, and so I'm taking the square root and thinking of it as p to the 1/2 and writing the exponent in front of the log. So 1/2 log p plus, again, 5 log q, and then minus, and I've got 1/3 log r plus 1, because that's the exponent of r plus 1 is 1/3. Let's do the next problem. This one's a little bit trickier, I think. You're combining all of this stuff into one log expression. Well, if I look at the inside stuff here, natural log of x plus 2, natural log of x minus 2, okay, that's a product of things. So I could, but I'm subtracting this whole thing here. So here's what I've done in my first step. I've taken the natural log of square root of 3, because the 1/2 is an exponent of 3. So natural log of square root of 3. Then this middle part here, I've distributed the negative 3 to each of these. All right? So negative 3 natural log of x plus 2 minus 3 times natural log of x minus 2. Just to kind of get it spread out there. All right, so I'm subtracting both of these things, even though it looked like a product right here, and it is a product, but this whole product is being subtracted, so this whole product will go on the bottom of the fraction. Okay, so I've got this single logarithm now, natural log of square root of 3 on top, and then x plus 2 times x minus 2, all to the 3rd power on the bottom. Now x plus 2 times x minus 2 does simplify down to x squared minus 4, so we could write this fraction this way. Natural log of square root of 3 over x squared minus 4 quantity to the 3rd power. Let's move on. I'm solving this equation, so the first thing I want to do is see that it's an exponential equation. My variable is an exponent, so I'm going to have to use logarithms to solve this. But first I want to isolate the exponential function. So divide both sides by 200. It gives me 0.065 on the left, equals e to the negative 0.0315x. Okay, well, I can take the natural log of both sides, and the natural log of e is 1, so this exponent here just comes down like this. So I got natural log of 0.065 equals this negative 0.0315x, so all I have to do is divide by negative 0.0315. So this is my exact expression right here. And then if I use a calculator, I get approximately 86.7736. So that was the instruction. Solve each equation, give 2 answers, one of them exact, and the other one accurate to 4 decimal places. Okay, so that's what we got right here. Rounded off. Here's my next equation. This is a log equation, which means I'm going to use the snail. 3 to the 3rd power equals x minus 5 squared. Okay, well, this one's not too bad to solve, because 3 to the 3rd is 27, all right, and then I'm going to take the square root of that to get the x minus 5 all by itself. So the square root of 27 equals x minus 5. Actually, it's plus or minus the square root of 27. So x equals 5. I'm adding 5 now to both sides. 5 plus or minus. And I wrote it as 3 root 3, but you could write it as square root of 27. Same thing. No big difference. This next couple of problems here where you're finding the domain. Remember, the domain of a log function is that which makes the argument positive. All right? So if 2x minus 1 is positive, it's greater than 0. And I solve this inequality, and that's my domain. It's easy as that. Let's look at part B. Part B is a little bit harder because this argument is a nonlinear expression. 16x minus x squared. Well, if I factor that out, okay, by seeing that x is common to both terms, I get x times 16 minus x is greater than 0. So the solution, or the domain of this, is the numbers that make this thing true. So those happen between 0 and 16. We'll get a positive product when I use a number between 0 and 16 in these two factors. So our domain is 0 to 16. The next one, 1 minus x is the argument. 1 minus x must be greater than 0. I will, let's see, what should I do? I'll add x to both sides. No, actually, add x to both sides and subtract 1. I've kind of done a bunch of stuff here. I get x is less than, because I'm dividing by negative x. Actually, this is a mistake here. This should be a negative 1 right here by subtracting subtracting 1 from both sides. And so I've got negative x greater than negative 1. When I multiply by negative 1 to get rid of the negative sign, I get x less than positive 1. All right? So that's a little bit of a mistake there. That should be x less than positive 1. That's my domain. Okay, let's move on to the last problem here about Danilo putting some money in a bank. He's got two choices. One of them is continuous interest at 2.85%, and this is the equation you would use for that. 3 years is our time frame, and that gives us a total of $49,016.77. And if I compare that to the other bank, which is compounding the interest 2 times a year, semi-annually, at 3.05%, that equation looks like this, and it's a little bit more heavy with the numbers, but it gives me $49,277.71. So this account wins. It pays a little bit more, pays about $260.94 more. So Danilo knows what to do. Okay, I hope you know what to do. All right, and so study this, and good luck.